All right, we're going to start our next chapter, and it's on electric fields. So today we're going to figure out what a field is and how it compares to gravitational field, which we already know. And we're going to look at some formulas and some key things that you need to remember. So to start with, just like gravity, right? Gravity can act between two objects that are separated. You don't have to be touching it to have a gravitational force. So the same thing works with electric fields. We don't have to actually have the charges in contact have an electric field. They can work over a large distance as well. So the idea in the old days of figuring out what happens when things aren't touching was a difficult concept for scientists to figure out, but it does make sense, right? How do we explain a ball that falls? Well, gravity's pulling it downwards. We don't see gravity, we can't really measure it, but we know it's there. And same thing sort of happens when we deal with electric charges. We know two positive charges are going to separate themselves, but we don't really see it or witness it because they don't touch. So a British scientist named Michael Faraday, he's the one that came up with the idea of a field, and he applied it for a lot of electricity and electrostatics and things like that. The way he defined it was, he said, a field is like a sphere of influence. So he used the word sphere because I think it was sort of dealing with Earth. So we knew that the Earth was a round sphere, and we knew that gravity was pulling it downwards no matter where you were on Earth, right? You could be at any location and you're going to be directed towards the center if we're talking about the force of gravity. So force of gravity is downwards. So we knew the gravitational field then has to be acting from all different directions. And a good example would be if you have a bad smell. So somebody has a fart or something like that. If you're right close to it, the fart's pretty strong. And the further away you get, the less and less it would be. So same sort of thing with gravity, right? If you're right close to it, the gravity's strong. If you're further away, it's going to be not quite as strong. So different types of fields, vectors and scalars. A scalar field would be something where we don't really care about direction. So if you're measuring the heat from a fire, you can measure it from any side of the fire, the top, whatever, you get the heat coming off the fire in every direction. And we would just say something like 55 degrees. We wouldn't say north, south, east, west, up, down, left, right, nothing like that. But a vector field does include direction. So for example, we normally say gravity. The gravitational field strength is 9.81 meters per second squared, and it's always downwards towards the center of the Earth. So you can see here, we're talking about the force of gravity, but the actual gravitational field is actually 9.81, which we know is our acceleration of gravity. So it's important to realize that a field isn't a force, it causes the force, right? So our gravitational field causes the force of gravity to be whatever, your mass times 9.81, but it's not the force itself. So the same thing happens with electric fields. We're going to have some sort of field around an electric charge that'll cause the field to go inwards or outwards depending on what the charge is, but it's the same sort of idea. It's not causing a force, or it's not a force, but it does cause a force. Okay, so next is how do we detect if there's an electric field and how strong it would be and whether it's positive or negative, all those kind of things. And the easiest way to do it would be to have some other known charge nearby. So if we had a charge that we didn't know, but if we put a positive charge near it, we should be able to figure out what the original one is, right? Because if this was positive and if our original is positive, then the force would be outwards. But if the original was negative, then our force would be towards it, right? They'd attract or repel. So that's how we're going to determine whether there is an electric field and what direction it would be. So we do have to be careful because if you have two charges, they're each going to have their own field and they'd interact with each other, and that might change things. So what scientists do is they made up a defined term called a test charge, and it's just an imaginary charge which, just for reference sake, we call it a positive charge. There's no rhyme or reason. It could have just easily been negative, but they use a positive. And we think of it as having no mass. It's too small to have its own electric field. So it's just sort of an imaginary, infinitely small test charge. It's kind of like when we talk about a pith ball, same sort of idea. So our test charge, we usually use Q, just like any other charge. But now we decide what's going on. So if we say we have a positive source and we put our positive test charge nearby, then we know that it's going to move away. right? So we know that the original was positive, the test charge moves away. If our original was negative, we know our test charge is going to attract. And I actually have these backwards. So that one is that one, and the first diagram is the bottom one. So if it moves towards a test charge, it has to be negative. If it moves away from a test charge, then the original must be positive. So let's do a quick example. So it says we have a steel ball that has an unknown charge. So that's our source. We have some sort of unknown charge. It says we put a test charge nearby, and we see that it moves away to the right. So obviously if it's moving away, the original had to be positive. So our original is a positive test charge. Okay, so pretty easy idea. So it's important to keep in mind that we're talking about our test charge as being the little one in the field, and our one that's creating the field, quite often we'll call it the source charge. So for this example, the steel ball is the source, it's positive. The positive test charge then repels and moves away. So our formula we use for electric fields is E equals force over Q. So our force is our electric force that we were talking about earlier in the last unit. So we could calculate this using Coulomb's law, K Q1 Q2 over R squared. So we could calculate a force, no problem. Q is, we're talking about a charge in coulombs. So that means our electric field is measured in newtons per coulomb. Right, if we just go force divided by charge. A couple of key things to be aware of with this formula. First off, the E has a little vector arrow above it. We must remember that that is for electric fields. In other formulas, we've had E for kinetic energy, potential energy, those kind of things. And that E in any of those formulas they don't have the vector sign. Okay, so in this case, when we have E, we're talking about energy. And for one like this with the vector arrow, we're talking about electric fields. Okay, so it's a little bit confusing because there's two E's in the two formulas, but you got to make sure you know the difference between the two. So energy will always never have the vector arrow. Electric fields will always have the arrow. The second thing to remember is the Q in the formula. So Q isn't anything special. A test charge isn't anything special, but we do need to remember that in this case, it's the Q standing for the object, the charge of the object, not objecting. So it's the object in the field, not the charge that's making the field. So in this case, if we were to calculate the electric field strength of the steel ball in example 1, we would have some sort of force that we'd measure, use KQ1, Q2 over R squared or whatever it is, and our charge would be that charge that's in the electric field, and then that's what would give us the electric field strength. Okay, so let's do another example. So it says we got a 3.7 Coulomb test charge, and we have another, so 3.7 test charge is 2.7 meters to the right, so we have another charge that's negative 7.94, and the distance between them is 2.7 meters. And it says there's an attractive force, right? One's positive, one's negative, so we know this one's going to get attracted towards it with a force of 3.62 to the 10. So the question is, what is our electric field strength? So pretty easy question, just plug in Fe over Q, so we'd have 3.62 times 10 to the 10. And our Q, right, we have to use the charge that's in the electric field, not what's producing it. So in this case, we would put in the 3.7 coulombs for our answer. Okay, so we don't use the 2.7 distance. We don't use the negative 7.94 for our source. Those numbers would be what would create the Fe, right? If we were to use Kepler's constants, KQ1, Q2 over R squared, not Kepler, sorry, Coulomb's law, we could plug all that into the formula, and that would give us the 3.62 to the 10. So in this case, our electric field is just that force divided by the charge that's in the electric field. So a couple things to remember. First off, when we're talking about this, you always got to remember that the Q is the test charge in the formula. Sometimes people get that mixed up. And if you ever forget, it's always good to sort of think that electric field works just like a gravitational field. So if you remember back to Physics 20, we had force of gravity equals mg. So if we rearrange that to be g equals F over m, it's pretty much the exact same thing as an electric field as our electric force divided by Q. So instead of a mass and a gravitational field, we now have a charge and an electric field. But the logic is exactly the same. So G, our gravity, or 9.81, was the gravitational field strength. So now our E is our electric field strength, so that'll be some sort of number in newtons per coulomb usually. Mass is our object that's in the gravitational field, right? We measure the mass of the person that's on Earth, not the Earth. So the same thing has to apply for electric fields. We want the charge of the object in the electric field, not what's creating it. So you can see it works very similar to what we did for gravity. So putting all this together, we know that from Coulomb's law, we're going to have some sort of electric field, and it's going to be different at different locations. But we also know that the direction will be different. So if we have a positive test charge, a positive source charge, its electric field will be outwards. Because if we put a positive test charge near it, it would get repelled. And a negative, then the electric field is inwards. Okay, so we draw arrows going all the way around. You don't need a lot of them, just enough to show that it's going from every direction. And the length or the size of the arrows will indicate how strong the electric field is. If it was a weak field, have short arrows. If it was a strong field, you'd make those arrows a little bit longer. So let's do a couple more quick examples. So the first one says a force of 2.1 newtons is exerted on a test charge when it's placed in the electric field by a different charge. It's asking if the force is pushing it west, determine the electric field. So we've got our test charge is positive 7.5. Our source is positive 7.5. And we have our test charge that's 9.2 to the negative 4. They're both positive. And it says we have a force of 2.1. So we know the electric field then is pushing it outwards to the west. Oh, I got my diagram backwards, but that's okay. So it says it's pushing it to the west, so our charge was actually over here going to the west. And it's asking what is the electric field. So we'd have E equals F over Q. So our force is 2.1 newtons divided by our charge of 9.2 to the negative 4. And I don't have my calculator on me today, but you could figure that out easy enough just by dividing those two numbers. And so therefore, your answer, whatever it would be directed outwards. So I just quickly checked it. It's 2.3 times 10 to the 3 would be the field strength, so newtons per coulomb. But the question is, what is the electric field strength at that point? So we know because it's positive, we know that our electric field is going to go outwards from it. But when we are that distance to the west, so if our charge was here, so we know at this point, our electric field then is 2.3 times 10 to the 3 newtons per coulomb, and then our direction would be west, because our point is to the west of it, and it's pushing outwards. So that's all you got to be careful about with direction. So example 4, we have the exact same sort of thing, except it says we have a smaller test charge. So instead of it being 9.2 to the negative 4, we now have a charge that's 3.7 to the negative 6. Okay, so it's saying basically the exact same thing. We have our test charge over here now, but it's a smaller test charge. So the question then is, what's the electric field? What's the force acting on it? So I already know that in that location, our electric field was 2.3 to the 3. So now in this case, we're just looking for force. So we'd have electric field times charge. So we take that answer, the 2.3 to the 3, and times it by our new charge of 3.7 to the negative 6. And that will give us 8.4 to the negative 3 newtons. So same thing, our force, because it's a vector, would be that answer, 8.4 or whatever it was to the -3 newtons, but now it's also going west because our force is outwards. So that's it with direction. Just sort of be careful where it's located to determine which way it's going. So now our last example is the same thing, except it's now saying we're putting a different charge in that same spot. So we do it the same way. So our force would be still the same electric field strength. The only thing that's different now is our force is negative 4.2 or 4.81. So we times it by 4.81 to the -2. So that's going to give us a new force, but because it's negative, our direction should be east, right? It's going to get attracted to the source, not pushed away. And if we do that calculation, we get 1.1 times 10 to the 2 newtons. So we have everything done right for these three examples. So pretty simple formula to work with. Just be careful of direction, positive, negatives, same sort of thing that we were doing before. So our last thing we got to look at today is now how can we combine this with what we already know. So we know our electric field is force over Q. But if we think back to our last chapter, we also know that electric force is K, Q1, Q2 over R squared. So we're going to assume in this case, just to make sure we have this straight, Q1 is our source charge and Q2 will be our test charge. So we're going to actually, in the formula, we're going to ignore Q2. So Q1 is our source. We'll just call it Q for a test charge, and that's the same Q that's in our new electric fields formula. So we can actually substitute these in, right? We can call it electric field. We'll put K Q1 Q over R squared and then over Q again. So you can see that basically our test charge cancels out. So we can get a new formula for electric field, which is K Q1 over R squared. And this formula actually works a little bit better because in this formula we're talking about the source, right? The Q1 in this case is our source that's making the electric field, which in a lot of cases is easier. And on your formula sheet they actually have absolute values around it, which just means we don't worry about whether it's positive or negative charge. We just solve our answer and then we use the direction of the electric field to determine which way it would go. Let's compare it to gravity again because it is almost the same formula. On your formula sheet in Physics 20, we had G, the gravitational field strength or acceleration of gravity, was big G m over r squared, where m was our mass of the Earth or whatever was creating the gravity field. And if we look at this new one now, we have electric field is K, kind of like our big G, Q1, which is our source charge, kind of like the Earth, divided by r squared. So we get basically the same formula now, just dealing with electricity instead of gravity. So one more example. So this one we have an object that has a charge of -3 to the -6. And the question is, what would the electric field be if you were 30 centimeters away? So we don't need to worry about a test charge or anything like that anymore. We just have our charge of the object. So -3 to the -6. So we know that because it's negative, our electric field will be inwards. And the question's saying, what is it at some point P that's 30 centimeters away from the charge? So we can use our new formula and put in K, 8.99 to the 9, times our source charge this time, which is 3 to the -6, and divide it by 30 centimeters, so that'd be 30 to the -2 squared. Plug all that into our formula. So we get an electric field of 3 times 10 to the 5 newtons per coulomb, and for direction we would say inwards or towards the center. Because it was negative, remember, our electric field goes towards it. So at point P, any point P that's 30 centimeters away, our electric field strength would be 3 to the 5 pointing inwards. And one last quick example. So what happens if we have more than one charge? So just like we just finished doing in the last unit, it works exactly the same way. So for this example, we got two negatively charged objects. The question is, what's the electric field strength that's exactly halfway between? So if our point P is halfway in between, what we want to do then is use the formula. So we'd figure out our electric field for the one on the left. So we'd have 8.99 times our 1.2 divided by, and our distance would be half of 0.58, so that'll be 0.29. Square that. And then we'd also do the same calculation for the other side. So we'd have our 8.99 again. This time our source charge is 3.9, and we're going to divide it by 0.29 squared again. So we don't have to worry about directions, just like we did before. That's why we're doing absolute values. We just want to figure out the electric field, and then we'll combine them just like we would with vectors. So in this case, if our electric field is negative, so that means point P is going to be pulled to the left. This one's also negative, so it's going to get pulled to the right. So we would just figure out those two answers and subtract them and combine them like we do with vectors. So if you get any kind of questions that have angles or whatever, it works exactly the same way. Just figure out each component and combine them using appropriate vectors. So for this one, we got 1.3 times 10 to the 11 for our electric field strength. For the other one, we have 4.2 to the 11. So we just need to subtract those two, and that will be our final answer. So if we subtract those, we get a net answer of 2.9 to the 11 newtons per coulomb, and the red one is bigger, so we would say to the right, or towards the red one, or towards the negative 3.9, anything along those lines. And that's it.